let's begin again here. Second half of class, we're going to focus on applications. I'm hoping I have time to look at all these applications, probability, motion, area, and average value is what that says, or function. Let's focus on the easier applications first. Let's focus on area and motion first. Put that down here. I've got the hot air balloon here. Again, from up, that we entered last time, let's enter it again. But now this time, let's make our velocity function be different. Something easier than this thing is. Though we can make it be something that we would need to integrate with substitution to do. How about t times cosine t squared? That would be an example of a function you could use substitution for. Let's make it even a little simpler. 2t times cosine t squared. If you were now going to integrate that with substitution, you would want to let w equal t squared. T is time here. dw would be 2t dt. Don't forget to add that extra dt and dx in the other examples. This is going to be our velocity function. When you integrate velocity, you get displacement is the best one-word description of what you get. Change in position is a more descriptive phrase for it. Although, if you want your position, you got to know where you start. Change in position is what the integral gives you. If you want your actual position, you got to know where you start. Are you starting at 0 on a number line when you're walking, say, back and forth? Or are you starting somewhere else? So there's our velocity function. Let's that's kind of a crazy looking function, huh? Wow. Okay. Let's make it over a smaller interval so we can see it better. Let's just go out to 10. That's better. Interesting. The oscillations are happening faster and faster. This is going to be kind of a crazy motion, I think. With this basic math assistant palette, you can do indefinite integrals. That's the lower left button right there. Zoom in on that. That's an indefinite integral and antiderivative. You can actually type the function here instead of the formula. By the way, notice that this is something to know that you do want to know. When you enter a function in Mathematica, you need to create a name for it. I called it v. I could have called it f. You put square brackets for your input, not parentheses. When you first define the function, you need an underscore there. And it's good practice to also put a colon before your equal sign when you're first defining the function. That is the function v of t. Is 2t times cosine t squared. I'm pretending this is the velocity of a hot air balloon. What's its indefinite integral? What's a general antiderivative? Let's imagine doing it in our minds here. Again, w equals t squared would mean dw is 2t dt. You'd be integrating cosine w and get sine w plus c. Sine of t squared plus c should be the answer. Is that what Mathematica produces? Actually, no! It forgot the c. Bad Mathematica. The creators of Mathematica know you should add the plus c, but they just expect you to do it. Okay? They expect you to do it. So there you have it, sine of t squared. This is a function that would represent the displacement, change in position, of the balloon. Though if the balloon starts at position 0 before moving up and down, I guess, you could also think of it as position height, essentially, if it started at 0, if ground level was 0. Which is the correct motion? Is this the correct motion? Yeah. I wish. Actually, the correct motion is basically just as crazy, but it is different. I can integrate the velocity to get the height. Essentially, this is going to start the height 0. I'm using an n integrate thing. I actually don't have to do that there. N integrate means numerical integration, like Simpson's rule, if you've ever heard that. Let me actually just do a regular integrate. The motion, let time go up to 10. Probably don't have to go so high. Is a lot of ups and downs, I think, still. But it's actually not the same motion. This is not the same graph, even though it looks similar. It's the graph of sine of t squared. Actually, this graph here gets higher in amplitude. Well, that graph is looking like it's higher in amplitude too. It shouldn't be. What is going on? I'm not quite sure what's wrong. I'm graphing. I think what's wrong is this should be an R here. Actually, that was what I wanted to happen the other day, but today I want something different to happen. Okay, now, well, you can't even see it now. Stop. Need a smaller plot range, I think. Is my balloon going to be too big now? I'm not sure. Oh, why is this taking so long? Sometimes Mathematica stalls. I don't know why it's stalling now. Maybe because the other code was giving it trouble. Okay, I'm not quite sure what's wrong. Okay, but we see the motion being the sine of t squared instead of 2t times the cosine of t squared. Not sure what's wrong. Okay, so that's a motion problem. Integrating velocity gives you displacement, which if you start at position 0 is the same as position. You can use integrals to find areas. Area under a graph, area between two curves. So we want the area between, let's say that's y equals x sine of x squared. Maybe it looks something like that. And some other function that I'm going to take to be simpler. Y equals, let's make it real simple, 100x, okay? And we're letting x go from 0 to 0.1. I'm trying to guarantee that the other function is above it. I mean, it will be, yeah. What's the area between those two groups? Integrating that one would require substitution. Integrating that one would not. The basic principle here is to find the area between two curves. You need to integrate the difference, top one minus the bottom one. That's really the only point I'm trying to make. And I'm sort of artificially making one of them a substitution problem. Let's just get the answer. The top one is 100x. The bottom one that I subtract in the integrand would be x times sine of x squared. And I, again, am artificially making that something where you need to do substitution if you did it by hand. So we do this with the substitution to help us, at least with the second part, and get the answer. And that will be the area between. It's about 0.5. Where x goes between 0 and 1. Sometimes you might have to figure out where the curves intersect. When it says find the area between them, and then you'd have to do some algebra to figure out where they intersect. I don't want to do algebra here. Question?
If the absolute value of if they intersect and they change, which one's on top and bottom? If you take the absolute value of
the difference,
the line minus the line, would that?
The absolute value of a difference of two functions will always be non-negative, so you get a graph that would always be above the x-axis. But yeah, you could do it that way if you're doing it with your calculator on Mathematica. But when you're doing it by hand, it's going to be best to see which one's above the other, so you know which one to subtract and avoid absolute value signs. What about the average value of the function? Let's put this in the context of an application. And remind you of some Mathematica code again. I'm now going to create a function that I'm going to call P of t. Again, when you create a function in Mathematica, you give the function a name. Mathematica's built-in functions always have capital letters to start with. When you create your own function, you don't have to use capital letters. I am, but you don't have to. You must use square brackets. When you first define the function, you must put an underscore after the variable. And it's a good idea to use a colon in front of the equals.
Wait, sorry, could you explain again why you put the colon in front of the equals?
I don't want to explain it. Just do it.
Okay.
Okay? It's called a set delete operator, and I don't want to explain that. Once again, I'll use kind of an artificial example. Even more artificial, put a 2 in front of it. So again, if you were doing a substitution, you'd let w equal t squared, dw would be 2t dt. The same kind of example over again. Just want to illustrate this in the context of substitution. What is the average value of this function over some interval? Let's make the interval fairly small so it stays positive. Say 0 to 0.1 again, how about that? Oh, I should maybe go higher. All right, let's go to 2.5. Actually, I was going to, initially when I created the P of t, I was going to think of it in terms of exponential growth. I was going to think about it as a population. This would not be a population. Let's not worry about that. What's the average value of this function over this interval from 0 to 0.5? Well, first of all, you have to know what average value means. What is the average value of a function? There's a couple different ways that you can think about it, and calculus books always describe it this way. It's the height of a rectangle, at least in the case where your graph is always above the horizontal axis, whose total area, like I'm shading here, is the same as the total area under this graph. I'll say that again. When your function is above the horizontal axis, like this is, the average value of the function is the height of a rectangle that you can make above the axis like this, whose total area, base times height, is the same as the area under the graph. And what that ends up meaning, because of the area interpretation of definite integrals, is that the average value of the function over some interval, x is between a and b, or t is between a and b, is 1 over the length of the interval, 1 over b minus a, times the integral of the function from a to b. Why does that give you the height of that rectangle that I described? If you multiply both sides of this equation by b minus a, you have just the integral on the right, and you have the average value times b minus a on the left. The average value is the height. B minus a is the width of the rectangle. You'd be saying average value times b minus a, height times width of the rectangle, is the same as the value of the integral, which would be the area of the curve. So you'd have to integrate this over the interval, in this case 0.5, and also divide by b minus a to find the answer. In this case, that's 0.5 minus 0. By the way, again, when you define functions, use the underscore, but whenever you use functions, do not use the underscore anymore. So basic things to know. You should know them about Mathematica. This should be the average value, but more importantly, and this is more important especially in multivariable calculus, where you're trying to understand the meaning of some harder kinds of integrals, it's a good idea to try to guess the answer ahead of time. What's the total area under this graph? Well, it's certainly less than the area of a triangle that you can make by following my arm here, and my hand over there. What is the area of that triangle? 1/2 base times height is 1/2 times 0.5 times, what's the height? 0.25. Trying to do that in my head. I think it's 0.0625. Certainly less. The average value is going to be less than that. The integral is going to be less than that. The average value would be less than that divided by 0.5, the interval. Less than double this. It's going to be less than 0.125. But more importantly, try to just approximate a rectangle whose area is going to be the same as the area of that. I don't know, perhaps right around there is a rectangle, the top of a rectangle, whose height is your average value. Maybe about 0.07 or 0.08. Let's see. 0.06. Also notice that 0.06 is closer to the lowest value of this function than to the highest value. It's closer to the bottom than it is to the top. That's because the graph is concave up. So it spends most of its time, so to speak, in low values than in high values. If you imagine t as being time. As time goes by, this function is mostly down low. It's only at the very end that it gets high. That's intuition as why the average value should be lower than halfway between the minimum and the maximum. I will try to re-emphasize that interpretation oftentimes, but that is a pretty important interpretation of average value. It's definitely very helpful if you take multivariable calculus, or in fact, in any science class, if you were doing a lot of integrals and trying to understand what they mean. The average value can help give some meaning and help you guess answers to see when you might be wrong. Give you ballpark answers. If P of t was a population, then the average value is the average population. Pretty simple interpretation in terms of real life. To end class today, though, I want to focus on the subject of probability. This is a little harder. Got about 10 minutes to do this today. I'm not just doing it today, but I'm doing it other days too. We're going to look at physics applications a lot in here, but we're also going to look at probability applications and something related to that, actuarial science. Have you heard of actuarial science before? Actuaries is a job, being an actuary is a job that pays very well. They typically work for insurance companies. They use a lot of math, and in particular, they use a lot of probability to model risk. Here I have a real-life situation, described with a lot of words here. It's going to be hard to wrap your mind around this, but do your best to really, really focus here. This is pretty important to me. We're going to try to apply calculus to probability, and the integral we have to do, you could do with the substitution. So here's the real-life situation we're thinking about. Let t be a variable representing how long it will be in seconds before the next car enters an intersection. Time after the previous car has entered. So you're standing by an intersection, watching the cars go by. A certain car enters the intersection. You start your stopwatch or your stop phone. What do you call it? Stop phone? Should I call it that? The stopwatch on your stop phone. As soon as that car enters, you hit the stopwatch, the clock, and you see how long it is till the next car enters. That's a quantity of time. You call it a variable like t. It's random. You don't know how long it's going to be. Could be 0.5 seconds, could be 3 seconds, could be 7 seconds, could be 0.1 seconds. It's governed by some randomness. You can see the cars coming, so you can make guesses, but if you close your eyes, except you're just watching that intersection, then it really feels more random. is called a random variable. And its value can be any number greater than 0. I guess you could say it equals 0 if the cars go through at the exact same time, but that would never happen. Its value can be any real number greater than 0. It's called a continuous random variable because it can take on decimal values, 0.1, 0.0356, 1.23987 seconds. You can't measure to arbitrary degrees of preciseness, but in theory, it could take on any continuous value. Not discrete, as in discrete math, not 1, 2, 3, 4, 5, etc., unless you round to the nearest second, which we're not doing here. This function, little f of t, 0.1 e to the negative 0.1 t, is an example of a type of function that can model probabilities related to t. For example, I might wonder the probability, the chance, that it's going to take, well, between 3 and 10 seconds for the next car to go through the intersection. That's what my ultimate question is. So I'm standing at the intersection, a car is about to go through, and I'm wondering, what are the chances that after that car enters the intersection, that it's going to take between 3 and 10 seconds for the next car to enter the intersection? Can that be modeled? Can that be measured? I think it can. And these kinds of functions are probably pretty good models for such a thing. And essentially, I'm just telling you the answer without explaining why. It's integrating that function that's going to give you the answer over this interval from 3 to 10. I'm not explaining why. This p means probability. The probability that t is between a and b is going to be the integral of this function from a to b. Probabilities in this context are always numbers between 0 and 1, like 0.2 or 0.3 or 0.7 or 0.9, though you can think of them as percentages. If the probability is 0.9, that's the same as 90%. It's a 90% chance. If we get a 0.9 here, it's a 90% chance that it's going to take between 3 and 10 seconds for the next car to enter the intersection. Okay? Is this a good model for a particular intersection? Perhaps. I am just making it up. Okay? But these kinds of models it seems to me, I'm not an expert, pretty reasonable. Integrating the function, again, is going to tell you the answer. Here's a picture of the graph with the appropriate area shaded. That area is supposed to be the answer. That's the integral of this function from 3 to 10. Looking at the scale, what's that area? It's hard to tell exactly, but that's a pretty small number there. It's not going to be a super big area because that number right there is so small. If you had to do it by hand, you could, and you would use substitution. Think about it with me here. Integrating this function, you'd want to let w equal negative 0.1t. Actually, you could even let w be just the positive 0.1t, but it would be simplest to be negative 0.1t. W equals negative 0.1t. Then dw would be negative 0.1 dt. 0.1 dt would be in there. The negative sign would have to be placed in there in the integral after you do the substitution. You are going to get a positive answer, though. It is a positive area. What area is it? Let's do the integral. Integral from 3 to 10 of this function f of t dt. The area is about 0.37. That would mean you'd have a 37% chance, approximately, it's a model, that it's going to take between 3 and 10 seconds for the next car to go through the intersection. What I want to end class on here, in a few minutes, is a simulation piece. Simulation is the key to understanding what this is about. I've got some Mathematica code that's going to help me do the simulation here. You do not have to understand this code. This is complicated code. What I want you to understand is the math ideas that I will highlight when I explain it. What this code is going to do is simulate the car is actually going through the intersection. Now I could try to make this in such a way that you literally see cars, like I had the hot air balloon on there. I could try to make an animation of that, but I'm not going to. Instead, you see the graph again, and you see a dot there. This first dot that you see is representing the first amount of time for the first next car to go through the intersection. In other words, a car has gone through the intersection, you hit the stopwatch, that dot is telling you that car took about 10 seconds to get there, into the intersection. When you run this simulation, it now simulates how long it takes more cars to go through. Each time you reset the stopwatch, you have to reset the stopwatch each time. It's like, you've got the car entering the intersection, you hit the stopwatch, the next car goes, and when the next car enters, you have to both hit the stopwatch to figure out how long it took for that car to get there, but also to re-zero it so you can redo it for the next car. If I step this forward by one spot, I see 3 dots. This black dot is at about 10 was the first car. This new black dot at about 7 is the next car. The red dot is their average now. And that's going to be the case as I keep going here. The black dots are going to be the amounts of time it takes for the next car to go through the intersection. The red dot is going to keep track of the average amount of time. So you see a bunch of black dots going all over the place, and you see the red dot kind of in the middle because it's the average. Most of the area is under this curve is in the lower values, like less than 20. Very little area is over here. So most of the cars take between 0 and 20 seconds. Very few take more than 20 seconds. Do they ever take more than 20 seconds? Yeah, and in fact, if you re-enter this, I get new data. Notice that first dot is no longer at 10, it's down at 4 now. It's new data. It's a re-simulation. I can play it. Well, there was one that took longer than 20. Once in a while, you get a car that takes longer than 20 seconds to get to the intersection. That one right there took almost 30. A couple of them are, or 3 of them are bigger than 20, 4, 5. That one has a lot bigger than 20, but still most of them are less than 20. Can I count how many of them? There are 100 cars total. How many went through the intersection? This will count how many. 34, close to 37%, which was the probability. 34 of them took between 3 and 10 seconds is what I'm trying to say. Close to 37%. Okay, these are pretty fancy ideas here that I'm trying to get across. I'm not just going to try to get them across today. I'm going to revisit them. You will eventually have some homework problems related to these ideas, but not right away. Okay? They are, in my mind, some pretty important applications of calc 2. All right, that's it for today. Thanks.